Good evening. In the last class, we talked about some of the large sample, which are also called as Z-test, and small sample, also called as T-test. Today, we'll look into the remaining cases of Z as well as T-test. We talked about two cases in the Z-test, Z-test for single mean, Z-test for equality of two population means. Today we'll talk about Z-test for single population proportion and Z-test for equality of two population proportion. And the methodology is same here. So whenever you want to conduct a hypothesis testing on the parameter, you will extract some of the sample items from the population. If you can extract all the items of the population, I mean data from all the items of the population, then no need to conduct the estimations as well as hypothesis testing. Whatever the value you have observed from the population, they give you the true picture of the population. So now I am interested in checking whether a population has a particular proportion for a particular aspect of proposition. Single population proportion. So we'll call or indicate this population proportion by P. So my intention is that the prevailing condition is that value P is equal to some value, say P naught, the proportion. Say it could be proportion of female births in that particular city or in that particular country or locality, proportion of voters in that particular state or district, proportion of defective items produced in a manufacturing item, proportion of patients who are cured, proportions of particular cases with respect to disease observed. So we have certain prevailing conditions, certain number observed from the past data. Now, because of some other reason, I'm suspecting that it has either gone up or come down, or it is something different from the observed value, which is P naught. So this is our hypothesis. So in order to prove this or validate that statement, we select a sample, and here we select a large sample N. Now, whenever you are talking about testing proportion or testing mean, you take as much sample as possible from the population, provided you can do so. If not, you have to select a small sample, and you can apply small sample tests like t-test and other, say chi-square test also, only if your population is normal. So otherwise, you have to go for tests which are called as non-parametric tests, where the assumption of normality is not at all necessary. Okay, so we have a population such that I can extract large sample from this population. So from the extracted sample, I'll compute the sample proportion. Now you know how to compute the proportion, right? So if you have n number of items totally observed, and out of which x are favorable, then we define proportion as x by n, or you could use simply any other notation, say a divided by the total. So this is proportion of A in that particular population or the totality. So statistically speaking, we use x by n, could use any other notation. Now this is the proportion, and by center limit theorem, we could say that since n is large, the mean of this or the proportion follows normal distribution with mean, the population proportion, and variance square root of the population proportion PQ by N. So this is a new statistic that we are discussing. So we are talking about sample proportion. Sample proportion is indicated by small p because I'm using capital P to indicate the population proportion. If you are comfortable with any other notation like theta, alpha, you can use that. So by the center limit theorem, I can easily say P follows normal distribution with P as well as the variance or standard deviation square root of PQ by N. This happens when N is large. what we mean is the mean of this actually follows. So it is E of P to be precise. Statistically, this statement is valid. E of E indicates the mean of a random variable. Here, the random variable, what we are talking is proportion. You can ask me, how can you define mean for a proportion? Now you have, say, looking into what called as proportion of type 2 diabetic in a set of patients. Maybe, monthly you are gathering the data. So this is the beginning of this year, say January. You have observed in your particular clinic or in your trial visits, you have contacted 100 people, of which 50 were type 2 diabetic. So in the first month, you have observed the proportion of type 2 diabetic people as 50%. Now you'll extract the same data on February, March, and so on. So you're recording a set of values for your P. So you can talk about mean value of that P. And statistically, that follows normal distribution when your N is large. Now, we have several cases here. Your N should be fixed. So every month you are observing 100 cases only. If you want to look into the variable value of N like 100, 120, then you have to, look into particular cases. So exactly here the actual distribution goes to binomial distribution. So in that case, you can look into binomial distribution and you can make your decision. Now to make things very much simple, we say stick on to a uniform sample size step. So this mean of proportion follows normal distribution with mean P and variance PQ by N, where we define Q as 1 minus proportion. So P indicates the proportion of people favorable to particular characteristic. Q indicates the proportion of people not favorable to a particular characteristic, and that is given by 1 minus P. Now, since we are testing for P, our P is a population value, it is usually unknown. Now, since it is a larger sample case here, you can have an estimate of this PQ by N, and that is the sample value. So you'll use the sample proportion to obtain an estimate of that particular value. So this is when you want to use the estimation case. Now sometimes, so when it comes to estimation of say hypothesis testing here, so in that case, we are testing whether the population proportion is equal to P naught, and the test statistic is always constructed under the assumption that H naught is true. So when we believe that this is truly happening, in that case, you can actually have the estimate value as P naught Q naught divided by your N. So standardizing this statistic, every standardization technique, obtain that particular statistic, subtract it by mean, divided by standard deviation. So you will have the test statistic to test this particular hypothesis as P, which is your observed or the sample proportion, what you have computed from your data, minus the hypothesis value, or this particular case we are talking, so minus P, and under the null hypothesis that P is equal to P naught, therefore it will be P minus P naught divided by square root of P naught Q naught divided by N, and this follows normal distribution with 0, 1. Now the rejection region is again based on the standard normal curve. For a left tail test, you will reject H naught. Left tail test happens when your H1 is of the form less than case. So you will reject H naught if your calculated value, so we'll call this as zcal, if your zcal is actually below minus k. In case of two-tail test, you will reject the hypothesis H1, which is, okay, so two-tail right tail test is the case when your alternative hypothesis is of the form greater than P naught. So in this case, we will reject H naught if Z cal is more than plus K, and we combine this for a two-tail test. So two-tail test happens when your alternative hypothesis is of the form not equal to. In that case, we reject H naught if our Z cal is less than minus K or Z cal is greater than K, provided the rejection region on both the tails has an area of alpha by 2. So here the rejection region will have area as alpha. This is about Z test for single proportion. You can have a look into various numerical examples available in that particular book to understand. I will not discuss much about the numerical problems for this section. So next you can extend the same concept for testing the two population proportions. So here the test exists. Either you can check for the equality or for any significant difference in the two population proportions. Now, since we are talking about two populations, now we will indicate the population proportions by P1 and P2. So I'll just give you the hypothesis. You can write this, or P1 minus P2 equals 0, or you can check for any significant difference test. So usually we conduct it for 0, but as said in a particular context related to a particular field, it is not always checking for equality. There could be some significant difference. So I could say the difference between P1 and P2 is 25% or 50%. So in that case, you can take this to be any particular value, say, let me write it as P. And then H1, so we usually do it for not equal to, in this case, or greater than, less than, or you can have P1 minus P2 not equal to P, less than P, or greater than P, provided you suspect the existence. Now the methodology is same. So you have two populations. So from each population, you will extract sample. I'll get N1 items from first population. I'll take N2 items from second population, which we call as sample. And for this sample, we'll compute sample proportion P1. And from the second sample, we compute the sample proportion P2. Taking the same definition, out of the selected N1, X1 is favorable to that particular attribute. And in case of second sample, X2 is favorable. You can have cases where N1 is equal to N2, not an issue. Now coming to the test statistic, we have Z is equal to our value P1 minus P2 in this case, or if you are looking into a significant difference of P, then you can subtract it by minus P divided by square root of the variance. So here we'll write this as P hat into Q hat into 1 by N1 plus 1 by N2, where P hat is the pooled proportion. That is proportion obtained from both the samples. So we have this as N1 P1 plus N2 P2 divided by N1 plus N2, and your Q hat is 1 minus P hat. So these many calculations are to be done when testing a hypothesis regarding equality of two population proportions. Now the rejection criteria remains the same here. So here, whenever you're applying, there is no knowledge about degrees of freedom is required. Only thing is you should look into alpha. So alpha for one tail test and alpha by 2 for two tail test. So please remember at least one procedure from the proportion, because we are concentrating on t-test to look into the test for mean and equality of two population means. So very rarely you can come across questions on z-test for mean, because t-test for mean is a compulsory part. We Therefore, you can expect questions on z-test for proportion and z-test for equality of proportion. Only the theoretical questions, no numerical problem. On the test statistic could be asked. We can give you the test statistic value and the table value and ask you to conclude. So such very simple problems just to understand your knowledge on what is your table value, what is calculated value, what is rejection region, or the entire process of conducting the hypothesis test for equality of two proportion, that could be also asked in detail. Okay. We also looked into three possible t-tests and two were explained. These t-tests are also called as small sample test, and you could apply this only if x follows normal distribution with some mean and the sigma could be known or unknown. Usually it is unknown because population is quite large. Known, and in those cases we require hypothesis testing, and we looked into three tests. T-test for single population mean. We looked into the procedure and we also looked into two worked examples. And then we have t-test for equality of two population means or difference of two population means. And there are two tests under the same heading. So this happens when we talking about a general case where samples are independent, like you have two entire different population and you are looking into the equality of the means. So you have males, a set of male patients, set of female patients, set of class A students, set of class B students. So variables are quite almost same x and y, but the population and the selected samples are different. The samples are x and y values, we generally call x values of first sample, y values of second sample, or x1, x2. They don't have any mathematical relationship. In that case, we say the sample values or samples are independent. Now, more commonly used t-test is t-test for equality or could say difference, and in this case, difference of two population means, provided the samples are dependent. Though you take samples using the statistical sampling techniques, you are talking about a case where samples are independent, and here we usually conduct this test for pairs of observations selected from the population, and hence it is called as pair t-test, and it is much often used in the cases where you are talking about a change related to some treatment. So when this happens, in most of the cases, we apply this test while we extract the data before the treatment, extract the data after the treatment. So we get pairs of observations and the test is called as pair test. So please concentrate on this part. Again, you will have a compulsory problem on this. Example 2 after the treatment. So it is not only under this case, you are not looking into related change. Even if you are looking into significant difference in the cases where you have set of marks of same students in say first test and second test. So you want to check whether they have the marks have improved, but no treatment between test 1 and test 2. In that case, you can apply this. But since the marks are from the same set of students, the samples become dependent samples. Now, similarly, you can talk about height of husband and height of wife, their respective wives. So you could come up with a regression equation and can prove that each data set is dependent on other. Similarly, age of husband, age of wife, weight of mother and weight of baby. So though the samples extracted from two different populations, you can talk about pair t-test there because we see some sort of dependency between the samples. But as said, it is mostly used to check whether a particular treatment is effective or not. And now we'll look into the construction as well as some problems of this particular test. So it is widely called as paired t-test. Remember, this is the test conducted by extracting two samples. You will select sample 1 before giving the treatment from the same set of people or items. Set of items or peoples are same. Now, you have extracted, say, n items before the treatment, but after the treatment, some items may, some people may die or some items may perish. In that case, what you do is you cannot extract the data for all those n people. You will only look into the pairs where you have sample 1 as well as sample 2 available. So you'll discard any such data, extra data available in sample 1. That is how the test is carried. Okay, so we have two samples. I have selected sample 1 items before treatment. So I'll call that as X, and I have the size n here. Since we are talking about pair, the size is same. I'll give some treatment. I'll record the values of Y with size n only. And then we define the deviation variable D, usually it is called as D, as X minus Y. And for this D, we compute the mean as well as the standard deviation. Now, if I compute the mean for sample X, it is indicated by X bar. X bar is equal to sigma X by N. Similarly, Y bar is equal to sigma Y by N. Now I have new variable D, which is defined as X minus Y. So if I'm interested in the mean of that, that will be indicated by D bar, and it is simply total of D values divided by N. And for that D, you have to compute the standard deviation. So let me indicate that as SB of D, or you can have D written as a suffix. Okay, so we have sigma D minus D bar whole square by N, the same definition of standard deviation. In case of X, now we have just D, but this is a time-consuming formula, so we have simplified that as sigma X square by N minus X bar square. Similarly, we'll have sigma D square by N minus D bar square. So this is the prior data and statistics which you need for the calculation, the computation of our pair test. So what is our interest is we are checking whether the mean before treatment is same as mean after treatment, or this is what is observed, or you could say mu1 minus mu2 is equal to 0 or is equal to some value. Let me say mu, let me take theta. So this is same as mu1 minus mu2 is equal to 0. So if you're not interested, or if your prevailing condition is that the means already have a difference, then you could see whether the difference has gone up or come down. Mu1 not equal to, less than or greater than mu2, which is alternatively same as mu1 minus mu2 not equal to, less than or greater than 0. Or if you are testing for this case, then you can have mu1 minus mu2 greater than, less than or not equal to theta. So whatever your alternative hypothesis, if you are using less than, it is a left tail test, greater than right tail test, not equal to two tail test. Now to compute this, we will be using the means. Usually we take X bar minus Y bar. Now since we are talking about the difference here, and the normal distribution is such that the sum as well as the variances in case of, say, dependent as well as independent produces normal distribution only. So checking the difference based on X bar Y bar is same as checking it based on the difference D bar. Can establish this result using the property of arithmetic mean. So X bar minus Y bar in the test statistic, what we have learned in the previous Z, that can be replaced with D bar. So this is the test statistic. It based on D rather than our X and Y. So this D bar divided by standard deviation of D divided by root n minus 1, and that follows our T distribution with n minus 1. So we have obtained the mean of D and we have the standard deviation of D. Now we can obtain the value of T. So I'll call this computed value as Tcal, and now we compare this Tcal with the values of K, minus K, and both minus and plus K in case of two-tailed test. So reject H naught if this happens for a left tail test, if this happens for a right tail test, and if this happens for a two-tailed test. Let us take an example problem. So I have some say marks values before and after coaching. I want to check whether the coaching is effective. And I have previously made the observation that the mean scores before and after coaching are almost same only. Okay, so that's why my hypothesis is mu1 is equal to mu2, or mu1 minus mu2 equals 0, because my past data and my past experience is telling that coaching is not effective because my means are same, but because of some reasons, the kids are sent to that particular coaching cases. That could be situation 1. Situation 2, you always know that there exists a significant difference in the coaching by an amount of say 5 marks. Okay, so what is this hypothesis telling? This is telling if your kids or if a set of kids go to that particular tuition or coaching classes, on an average, their marks are high compared to the students who doesn't go to coaching. So if they go to coaching, on an average, they get 5 marks more than the marks compared to before coaching. So if you are testing this case, then you will have mu1 minus mu2 is equal to 5, and that was our theta. And I forgot to write the theta there. So if you are interested in selecting theta there, then you can have fine. So in that case, it will be d bar minus theta divided by sd by root. Okay. So to make things simple, I'll just look into the case where significant difference is 0. Now my belief is that the coaching has made enough efforts in changing their existing behavior, and students who are taking coaching have significantly observed to score more. So my hypothesis will be before the coaching the mean is less compared to the mean after coaching. So I have mu1 less than mu2. If you have taken your x as marks before, marks after, and y as marks before, in that case your mu1 will be marks after, mu2 will be marks before, and then your hypothesis will be mu1 greater than mu2. It becomes a right tail test. And then, so whether you start your test by taking x as before or x as after, the test procedure and your conclusion remains the same. Only thing you will observe the difference in the sign of your D. So if you have taken this and if this is really happening and if it is significant, you will observe significantly negative values in the D. If you have swapped x and y, you will observe positive values in the D, positive cases for right tail test, negative cases for left tail test. So the test procedure doesn't change, it remains the same. The conclusion is also same. Our test statistic is P is equal to D bar divided by standard deviation of D divided by n minus 1. So we should compute the values of D bar as well as standard deviation of D. So first I need the values of D. D is defined as x minus y. And to compute the standard deviation, I need D square. So 50 minus 60, 10, I have 1, minus 10, minus 1, minus 1, minus 5, minus 5, minus 10, minus 1. So this is my D. I'm computing D square. Okay. I need the total of this. So sigma D 10, 20, 30, 35, 37 minus 37. N is equal to 7 pairs. Then 1, 2, 3, 2, 75, 76, 77. So this is our D square. Now we'll compute the values of D bar. D bar is minus 37 by 7 and standard deviation of D indicated by SD is sigma D square by N minus D bar square. So 277 by 7 minus the mean square. So 37 by 7 produces minus 5.2857, and if I consider that 5.2857 and obtain standard deviation, 277 divided by 7 minus 5.2857 square. Comes to 3.4107. So we have the mean of the difference score as minus 5.27 with the standard deviation of 3.41. So though you observe that the average difference is around minus 5, you can't just conclude, yes, the coaching is better, because if you look into the standard deviation, it is telling the difference could be, anything with respect to 3. So you could have mean plus or minus 2, mean plus or minus 3, plus or minus 1 standard deviation. And since we are working under the normality nature, so your D could actually take any value within the 3 sigma belt. That is, if you're talking about x plus or minus 3 sigma or mu plus or minus 3 sigma. So when I say 3 sigma, it is around 9, and plus that indicates a 4, which is with respect to this a minus 4. So you cannot just take a call here just by looking into the value of D. So that's why we actually do the hypothesis testing. So as said, it could be just by a chance because of the sample. We are checking whether is this significant. Now to make you understand simply, on a particular day, I have consumed 3 chapatis, but that doesn't mean that your average consumption is 3. So it could be 2.5 or 3.5. Because of chance, that particular day you have consumed on an average, say 3 chapatis. That is what we are looking at. Okay, so when I look into the values of D bar and SD by substituting that here, 5.2857 divided by 3.4107 divided by square root of 6. 7 minus 1 is 6. That is the degrees of freedom. So I'll take this as P value and we call it as theta. So I have minus 5.2857 divided by 3.4107 divided by root 6. So that comes to minus 3.796. 1. Okay. So now it's the time to define your type of test, and this is less than, it is a left tail test. Now this procedure also important. Whenever it is a one tail test, will have level of significance or probability of type 1 error, which is alpha to be 5% or 1%. So that means now in the table, you have to look into a table with column 5% or 1%, where your degrees of freedom is n minus 1 is equal to 6. Now, as said, for you in the examination, 2 or more table values will be given along with the question. The entire table is not provided. So you have to concentrate on the table value where you have degrees of freedom 6 and alpha given as 5% or 1%. And accordingly, you define your level of significance in your problem. So first see what table value is given. You see what is the number of observation. Number of observation minus 1 is the degrees of freedom. So if by accident two table values both say for 5% and 1% and with 6 degrees of freedom is only given, then you could select either and you could conclude. And there could be cases where table value for 5% but 7 degrees of freedom will be given, or and 1% 6 degrees. So 5% 7 degrees is not valid for this problem. 1% 6 degrees is the valid table value. So you select that and you will conclude the problem. So always look into the degrees of freedom and the given table values. Just invest some time, use your knowledge on degrees of freedom and the table value, then decide which to pick. So now I said I'll look into 5% as well as 6 degrees of freedom. And if I look into that, take the table. And 6 degrees comes to be 1.94. But since it is a left tail test, I have that as 1.94, and we indicate the table value by P alpha, and alpha will be specified. I mean you have taken it. So we start our hypothesis testing